Okay, hello guys. Okay, let's start the session. Okay, today we look at this December contest. Okay, yes, it's really hard. Okay, the hard part, the tough part is that these three problem is not the algorithm problem. It's not about find the DFS or the component. No, it's just you know we can call it AD hoc, or you just need analysis. Okay, you need analysis, find a way to do that. So it's something like the math problem. Okay, it's not the algorithm. You need analysis how to do that. Find a greedy way to finish that. There is some skill you can use the inside that, such as map, set, or the postfix, prefix, something you can use. But basically, there's no algorithm. Okay, this problem is not algorithm problem, so it's difficult. Okay, sometimes we use stack. That's common. Okay, lots of guys is stuck because he just cannot figure out the way to do that. Okay, he cannot figure out that. So how we do that? There is no either way to solve such things. The only thing is that you need a practice lot. Okay, we need to do a lot of. We already learned the algorithm. We learned the data structure. So now the thing left for you guys is just practice. If you practice more problems, you can have more experience. So next time you see such problems, maybe you can figure out the way to do them. Okay, and let's see these three problems. So the first one is for the tower. Give you some course. And one thing to be careful is that each weight, this is weight, there is 4 core, the weight is 9. But, see here, the numbers of each group is a huge number, right? Is these things. And also you have n groups, n is also a huge number. So that means totally, if you count by cores, each core, you figure out on each core, it will time out. Because totally there may be, 2 times, yeah, the number of cores is this number. So the first idea is that you cannot figure out your algorithm is based on each core. You must based on each group. That's the first observation we got, okay? And another observation you can get is that, here we need a tower, maybe, for example, for these 3 cores, you can use this 9, the weight 9 core as the bottom. Then maybe weight 7, weight 2. This is a tower, okay? The bottom one is the biggest one. And the difference, you can only put, the cores with weight smaller or bigger or equal, smaller or equal than this number minus this key. So if the base one is 9, you can put 7 on top of it. You can put 6 on top of it, right? But you cannot put 8 on top of it. There is a different requirement. And I mean, the second observation is actually, if you put the biggest one on bottom, and the smaller one on top, you find how many towers, how many cores you can put on these towers is just as same as you put the smallest one on the bottom. You put 5 on the bottom, then you can put another core, maybe the size is 7 or 8 or 9. All this weight can be put on that. Okay, if you put 7 on top of it, you can put 9, 10, or 11, all this on top of it. So I mean, you reverse the order, the answer should be same. So the requirement asks you get a tower that the bigger one is on bottom, the smaller one on top. But you can also do this in another way. The smaller one on bottom, the bigger one on top. It's easy to understand, right? If you can find this tower, such tower, the biggest on bottom, you just reverse it, right? You go to from smaller to bigger one. So the answer is same. So that means why we do this one? Because if you use set or map or something, by default, the order is from smaller to bigger, right? So that means sometimes maybe you can use this way to make your algorithm easier. Okay, that's two observation, the first observation. Okay, then let's find how to do that, right? You give you groups, okay? The 9, the 7, something. Maybe you can use these numbers, okay? Or you can just create, a simple input by yourself. That's a way, okay? For such non-algorithm problems, we always can create lots of numbers, lots of test case by ourselves. Then we observe how to do that, right? We find the way, okay? If we only use this simple input, maybe you cannot figure out your algorithm. So you need to create more numbers, okay? More test case to validate, to figure out the patterns beside that. Because the simple input is too easy, okay? Maybe you cannot find something. For example, I will create something. I like key is maybe 3, right? The difference of two cores need to be bigger or equal than 3, okay? I create some numbers. Maybe, there is one group is 10, and you have 5 cores. And there is another group, the size is 7. There is maybe 3 cores, and maybe there is a course size is 6. Maybe there is 2 cores, and maybe there is the size for 3 or 4 something, okay? And there is maybe 10 cores. And here you can define any m. Maybe you just figure out for these 4 groups. It's 4, and m. Think about if m is 2, what we can do, right? If m is 2, maybe you can choose this one, this one. Yes. If m is 3, what we can do? If m 3, you see, we can choose this one. We can choose the tower as 3, 10, and on top it is 3, 7, and on top it maybe 3, 3. We can do this way, okay? So totally we find 9 cores, right? 9 cores. Okay, then we just figure out, we just use other numbers. If m is 4, what we can do? M is 4, this is m is 3. If m is 4, what we can do? We can use this one as the bottom, but there is 5 cores, it's enough cores. So you can go to this one, 4 cores, right? You can go to 4 cores. But if you go to 4 cores, you find that, okay, this is 4 cores, but if you want to put this 7 on top of it, there is only 3 on top of it, right? 3 on top of it. That means, okay, maybe here the thing come out, okay? Some idea you should have. Okay, I should have 3 cores on bottom, right? So after you have 3 cores on bottom, here you have 2 cores left, right? It's like this way. And then, of course, you should put this on top of this one because this 6 is too huge. So we put 3 on top of it, 3. Okay, we got this tower, we get 9 cores. And you see, okay, there is still 2 cores left here, right? For this 10. So here, there's some greedy idea. You can try that. You always want to the bottom as bigger as enough, right? If there is a 10, is a 7, or there is a 9, something size, some size, we figure out that, of course, if there is 10, you should put 10 at the bottom of the tower. That's greedy, right? Because this is easy to understand. You can try from all these numbers, you find that. Because the bottom, as bigger as you can, if the bottom one is bigger, you can always put the more cores on this tower, then you put a smaller one as bottom, right? That's greedy. You can put, if you put 9 as bottom, then you go to 9 cores. If you put 10 as bottom, you can go to at least 9 cores, maybe more than 9, right? Because you have more opportunities. So that's the idea, okay? You need to have this observation. If you can't figure out this one, you cannot do this problem, right? Guys, you understand what I mean? So the priority is to choose the biggest one as a bottom. You always choose the biggest one as bottom. That's what we need, okay? We choose this biggest one as bottom, and we can put some cores on top of it. And the same idea, the second one, here, you can choose 6, you can choose 7. Of course, we should choose 7. Same idea. You choose 7 as the second one. For the third one, you have more choice, right? Compare with 6 here. Of course, 7, you have more choice. Even 4 you can put here. If you put 6 here, you can only put 3, size 3. You cannot put size 4. So the same idea. For each one, you should choose as big as you can. If there is more choice, you always choose the biggest one. Okay, this is the first tower. After you finish this round, this turn, you find, okay, there is a turn. Okay, still 10. You can build another tower. This tower, you use 10, right? You use 10. But for this 10, you see, okay, there is 2 cores, size 10. But you only have 1 tower left. You can build another tower, right? You cannot build 2 towers because here you build 3 towers. Okay, so you build this tower with number 1, right? Only with number 1. And so we have some idea. When you build tower, there is some relationship with this M, right? You need maintenance M. You build 3 tower, this M can mean as 3, right? So each time, what you can build, here you can build 3. The group number of this tower is 3, right? You can build 3 tower. Here, you can build 1 tower. So each time, how many tower you can build is decided on 2 factors. One, M. Another one is how many core in each group. Something like that, right? We may have some idea. So here, you build 1. This tower numbers is 1, not 2. Even you have 2 size 10 cores, you can only build 1 tower because M is 1. So here, maybe you think about there is some mean function here, right? You need to go to the minimum number of M and the current group numbers. So it's 1. Then you just choose on top of it. No, you see, this one, you shouldn't choose this 7 again. Okay, so here is the idea. I cannot choose 7 again. How do I know I cannot choose 7 again? So last time, if you build this one, you should change this to 0. Maybe you should remove this core, right? The best way, maybe you should remove this one. So this time, turn 1, you find the next one should be this one, 6. Okay, so 6. 6, there is 2 core here, but we should only use 1. Okay, we minus as 1. There is 1 core left. We should use 1. So here is still another function of mean function here, right? So if you have 10, 1 core, and 6 has 2 core, you should build 1 tower rather than 2 tower. It's easy to understand, right? You have several group of cores. If you want to build a tower, how many tower you can build, use this cores is a mean number between these core groups. Okay, so 6. Then you choose this one. There is enough 3, so you can build 3, 1. Okay, you got your answer, right? You can use other numbers, other input to validate this one. Okay, you can also create other ones to validate this one. Because this one maybe is not good enough, then maybe you didn't find the algorithm. Let's change something, okay? Still have this course. And we have M. We can still build M is 4, K 3. But here, we may let the bottom smaller, right? So last time there is enough 10 for you to build. So maybe it's not easy to find the pattern. No, we think that there is 2 cores with size 10, right? And maybe there is 5 cores with size 7, maybe 3 cores with size 6, and maybe is 4 cores with size 3. Okay, this is size, this is size, this is number, how many. Okay, this can be called weight. So how we do this one? Let's use the same way to do that. And the first way is that you want to build the bottom as 10. Why? Because the biggest one is 10. Okay, so we build 10 and 2 of them. Why 2 of them? Because there is 2 cores with size 10 and your M is 4. The mean number between them is 2. So maybe you can build 2. Okay, you build 2. And okay, sorry, I want to change this number. Okay, maybe I want to change the number. Okay, you can try different number. Okay, I just want to change this. You know, maybe you try different as this one. Okay, last one you already try that, and I may try this one. So this is 2. Okay, then you put this one, but the next time you put this one, 7. Okay, but 7, there is only 1 core with size 7. You know, 7 difference with 10 is 3. So you can put 7 on top of 10. But you can put 1. So that means you cannot put 2 10s here. So you should change this to 1. Right? You should change it to 1. Okay? So that means if you build the tower one by one, maybe you cannot just, you know, at the beginning you find that there's 2 cores with size 10. Then you think that you can build, you know, 2 group of towers. One way, you know, there is multiple idea. Maybe one idea is that, okay, I shouldn't, you know, decide this number 2 here. And maybe I can just, you know, leave this here. Okay, maybe I can build, you know, I know there is 10. I know there is 7, right? But I don't know how many. Okay, and after 10, 7, you choose the next one. Next one cannot be 6. 6 cannot put on 7. You can choose this 3. Okay, so I build 3 on top of it. Now I know how many I should put here. Why? You find 2, 1, 4. So the smaller number between them is 1. That means this tower, you know, this tower group, we see this group. This group number should be the smaller number you choose, right? So it's 1. So this may be an idea, you know. Maybe I can choose the first one, biggest one, then I can find the next biggest one whose size is smaller or equal than 7, because key is 3, right? There is 6, 7, 3, both smaller than 7, smaller equal than 7, but I should choose a bigger one. So I can choose this one. And then you decide the 7 is the second one, you choose the third one. The third one should have the size difference with the 7, at least key 3. So we choose this one. After you choose this 3 one, you go to the mean number between them is 1, right? How many of each group? This is the size. You choose size, and you choose these 3 group cores, and their numbers 2, 1, 4. You got mean number is 1. Then maybe you can do it again, okay? Then you know it's 10, it's 1. Tower number is 1. So you choose this one, 7, 3. You build this one, you count, okay, I got 3 cores, and I can minus this with 1, minus with 0, minus this with 3. Okay, so that's the first turn, okay? The first turn, turn 1, you got this one, you got 1 tower, 1 group tower, right? And after this one, you can do the same thing. Okay, you build the turn 2, you build the 10, okay? And you shouldn't choose 7. Why? Because 7 is 0. So how we choose this one? Okay, we think about it. This is 0. Maybe we should erase it. Okay. So if you do not erase it, think about, if you want to find the first one, you know, bigger equal than 7 or smaller equal than 7, you still need to find this one. Although you check, okay, the number is 0, then skip it, find the next one. Think about if there is a lot of group, their numbers is 0. Of course, it will cost lots of time. You should have this idea. Okay, so this one, if we can erase it easily, that will be good. Okay, so we can erase them. How we erase? We leave it. Okay, then you find the next one is 6, so you put 6. And you find the next one is 3, you put 3. And this 3 number, 1, 5, 3. The smaller number is still 1, so 1, 1, 1. Then you minus this with 0, minus this one with, with 2, minus this one is 4, you change them. This is turn 2. You build 2 towers, right? You got 6 cores. Okay, because the M, you change to 2 because you build 2 tower. It's still not 0. So you should continue to do this one. So here you have some idea. Maybe your loop can be something like while M not equal to 0. You build some tower, right? You build some tower and you minus M with some numbers. You add some cores on your answer. This is your basic logic. Maybe this is one way, right? You have some idea. Because through this one, we know when M is 0, we should stop. Okay, so here the turn 3. I mean, in this while loop, you do the next loop. Here, we already remove this one. Why? Because 10 is 0. If it's 0, when they change 10 to 0, you find it's 0, you just remove that. It's easy. Okay, think about when we remove that. Okay, so next one, the biggest one now becomes 6. So the base of this tower is 6. And on top of it is 3. We don't know how many. How many? See, 3, 6. Their smaller number between them is 2. So that means if you use 6, 3, you can build 2 towers. And also you need to check the M. M is 2, right? You still need to build 2 towers. Okay, that's good. There is 2 towers left. So this number is 2. So how many cores, how many towers you can build in these turns actually depends on the smaller number between these cores and the M, right? You need to find the minimum between them. So 6, 2. So change this to 0, change it to 2, and you remove this one. Okay, so you add 4. So you got your answer, right? You can validate this is right. Okay, maybe you think, okay, maybe at the beginning I should build 5 towers. I still need to build tower. That's okay. So if after you build this 1, 1, 2, 4 towers, M is not 0 because no M is 5. So you need another 10. Another 10, you look at it. Okay, you only have 6, right? Now you just build a tower 6. And you cannot find any number between on them because there's no non-zero number which smaller than this 6. So you just build this one. And you should build how many? You have 6 cores or 2 cores with size 6. But you still need 1. Here M is 1. You still need to build 1 tower. So this number is 1. So you add 1. Right? So you finish that. Okay? So this is what we just do it by hand. Okay? So this is not the best way. But this way, okay, I have tried. If you use this way, it's easy to understand. And you can pass most of the test case. Only 4 test case time out. Okay? It's still time out, but you can do that. Only 4 test case time out. That's a good enough, okay? Because totally there is 17 test case. If you only have 4 test case time out, that's good, right? That's good, okay? And this no, we have this idea. This is just simulation, okay? No skill here. It's very easy to understand. We just use some advanced data structure to implement that. So the key logic is while M is not 0, you build some towers and you add to n's, you minus something. So how we build tower, just like this turn, each turn what you do, right? Each turn you check, you want to find the biggest one, right? In this tower, let's go back here. At the beginning, you have this tower. Okay, this is a 4, 5. So what you do is here. This logic is how you build them. You need to design a good data structure. You need to choose a good data structure for it, right? Choose a good data structure for it. So how we build that? Okay. What we do? Just simulate that. We need to find the biggest one on count groups. You have 4 groups, right? And you need to find the biggest one. And you need to find the next one. The next one is what? You find the biggest one is 10. Next one should smaller equal than this 3. Smaller equal than this 3. Okay, smaller equal than this 3. And smaller equal than 10 minus 3. Smaller equal than 7. There is lots of numbers. Both these 3 numbers smaller equal than 7. But you need to choose the biggest one. Okay. And after that, you just choose next one, which should smaller equal than 7 minus 3. After you choose these 3 groups, while you are checking these 3 groups, you know each group number 2, 1, 5. And you know the mean number between them is 1. So you compare this minimum 1 with m. You decide this time how many groups, how many tower you build. You got these 1 numbers, right? You got these 1 numbers, you can minus them from these numbers. Minus them. And after you minus, for example, this one minus 0, if it's changed to the 0, you can erase it, right? And after you do this one, this number, nth, is easy. Nth should add with the group number and how many core you find. You find 3 group cores, and you know the tower number is 1. So you add 3 times 1 actually, right? That's a basic idea. Then how we do that? What's that structure we need to implement this one, right? See, you need every time you need to find the biggest one, right? And maybe okay, let's begin. Every time you need to find the biggest one, and every time you need to find the first one smaller equal than the last one minus k, right? You need to find the first one smaller equal than which number, and you need to erase some number. Of course, we shouldn't use vector. If you use vector, you erase it. It's difficult, right? It's costs most time. We shouldn't erase in the vector. And every time you need to know the biggest one, count the biggest one is what. So guys, what that structure support this is the best choice for this one. Do you have some idea? You want to know the biggest one, and every time you want to find the first number bigger equal than some number, right? What's that structure you have? Although this one need to figure out no specific algorithm, but the basic the knowledge we have learned, we can use that. That means you have the idea, you want to run faster, you need to design the good data structure. So what is this good data structure, right? We know what we want. Then, according to this scenario, we should choose the data structure, right? We should choose the data structure we need. Okay, so of course, guys, do you have some idea? This scenario, do you familiar with this? Are you familiar with this data structure? Yes, Ethan is right. Of course, it's a set, right? Set is order. And the set, if you erase someone, it's log n, right? It's faster. And the set, if you already save something in the set, if you want to find the first one bigger equal than something or smaller equal than something, you can use low bound or up bound, right? It's very easy, guys. It's still log n. So that means if you use set here, every time you choose a tower, or you erase someone, or you change someone, it's log n. Okay, it's faster compared with vector. Okay, but here another problem is that if you use set, maybe it's not easy here because we know the set by default is from smaller to bigger, right? So if you save them in the set, this one will be the beginning, this one will be the last one, right? It's in this order, from smaller to bigger. You can save this each group as a pair in the set. Then the set will ordered by the first one by size, but it's from smaller to bigger. Here, our logic is every time we choose the first one, I want it's the biggest one. So that's okay. I just explained. You should find, of course, you can define the set ordered from bigger to smaller. But that's also difficult because when you use low bound, right? Our low bound, upper bound is to find the first one bigger, equal than something. Here, if you ordered from bigger to smaller, you want to find the first one smaller, equal than 7, not bigger, equal than 7. Maybe it's, it's not easy. So we use what we observed at the beginning that, if you want to find the answer, build such tower. It's the same answer. You build the tower like, this order. You choose 3 as bottom, 7 on it, 10 on it. You choose 3 as bottom, 6 on it, 10 on it. You choose 3 as bottom, 6 on it. It's the same. I mean, each time we just change this algorithm. Each time we just choose the smaller one as the bottom. Then we choose the next one bigger, equal than this smaller one plus key on top of it. Then we choose the next one is the top one plus key, bigger, equal than the top one plus key. Then we got that, right? So we just finish this algorithm, right? We just translate to the C++ code, right? We save all this group in the set, and the first one is the size. Second one is the, each element in the set is a pair. The first one is size. Second one is the number of this group. We save all this group. Then you just use a while loop. The basic logic is a while loop. While m is not equal to 0 is a simulation. We just build tower. We use greedy to build tower. How we build them? This build logic is here. We reverse this one. We choose the smallest one, right? And we use low bound because you want to find the first one bigger equal than that. We use low bound to find the first one bigger equal than 3 plus 8. So maybe it's not this one. If we change the idea, we change small to bigger, maybe you should choose 6, okay? But the answer is same. Then we choose the first one bigger equal than 3, and then we choose the first one bigger equal than 6 plus 3, 9, bigger equal than 9. We choose these numbers, we got the mean number between them, compare with m, we got the tower number in this turn. We know how many times we build this turn, and we know in each group we should minus what. Here, if this tower number is 1, we just minus this one with 1, minus this one with 1, minus this one with 1. And if we minus this 7 with 1, change to 0, we just erase that. It's easy to erase 1 in set, right? So next time, if you choose, you will not choose this 7 again. Because set, think about that. The set continue change smaller. So the time complexity for this one is not easy to estimate, but you have some idea, you change that, right? The set continues smaller, smaller, smaller. So it will be run faster. So that's why I erase that. If you do not erase that, you find the low bound, you find the 7, okay, it's 0. Then you need to find the next one, right? Maybe there is lots of cores. Their numbers is 0. Then you need to loop them one by one until you find a non-zero group. That's, that is not the best way, okay? So that's a basic idea. Okay, then congratulations, we got the, first version of this program. And guys, are you okay with this algorithm? This algorithm, I think, is easy to understand. It's just simulation. Just build the tower greedy, right? Each time, choose as many as towers you can build. I can build 2 towers. I can build 3 towers or 1 towers. I just choose the biggest one or smaller one as bottom and then build until this while loop finished. Okay. So this m is a big number. So, but this loop will not run m times because, the worst case is that each group only have 1 course, then you may, run this loop m times. Okay, right? M times. That will be timeout. That's the only, timeout situation that all these cores, you have only one course for each group, or their size. So each time after this, each turn you can only choose one course. If the given input is each time, you can only choose one tower. You can build one tower, right? Each time, like this one, no, not two, one. Each time you can only build one tower, no matter how many cores inside that. Then this while loop need to run m times, because m is this number, so that will time out. So that's why this program cannot get, full correct point, because special input, okay? But in most of the case, you can always find more than one towers each turn, because each group, right? Okay, each group has more towers. Okay, so how we do this code? I have some code here. It's very easy. Okay, it's very easy. Okay, here you can use set. Here I use map. Okay, map set is same. Okay, actually set is more easy, but of course you can use map. If you use set, you need to save a pair, right? For each group, the size, the numbers. Here I use map, so I set the weight, the size of each core as the key, and the numbers of this group as the value. So this key value pair is just like what you saved in set. It's same idea, okay? Same idea, okay? Because the set map is what? Map is it's very similar like the set, right? Map key value is a pair. Think about that, right? But inside the map, each key and value is a pair. It's just like a set you save the pairs, okay? So the idea is same, okay? So what you can erase something in map, or you can erase something in set, or you can use low bound, upper bound in set, then you can use low bound, upper bound in map. Similar, okay? I build this core. Remember, core X is how many core with this weight, this size X. Then I just use this while loop. You see, while I am not equal to 0, right? At the beginning, I save all cores in the map, right? This A size has B. B cores has A size. Then I use this while loop. And then each time I go to the beginning. Beginning is the smallest one. Here I build the bottom as the smallest one, okay? I go to the smallest one. The smallest one's value is how many core? How many cores in this core group, in this size group? Then I just do this one. I go to the heat, the size. For example, the 10, okay? The size of these cores. I just use this while loop, do what? You see, continue use loop bound to find the next one bigger equal than count weight plus key, count size plus key. I find it, okay, until it's big end, right? Until you cannot find. If I find, I go back here. This is while true loop. I find the next one. Each time I change the count heat. This heat is actually count top, the size of the top course on your tower. Each time I find the new heats plus key. I find all of them. This loop actually is to find how many core, how many size you can put in this tower, and this number is that the smallest number between the group numbers. You have 4 10s, 3 7s, 2 3s. You choose these 3 ones, but you know the minimum number you can put is 2, right? This number is the minimum number of the group core numbers. You know this one, okay? Then we do this loop again. It looks stupid, but the time complexity is same. You just do it again, okay? But this time I still use low bound to find the next one, right? I still use low bound. Same logic like this one. It's same logic. The only thing is that here I just find the minimum number. Here I know the minimum number is what? I just minus that number. Right? And each course I minus that. After minus, if it's 0, I erase it. The only thing I change is this one. So after this turn, you know how many cores, how many towers you can build. You can build is this num. This is the smallest number between all the cores, all the core groups, and you know the tower size, right? You choose 10, 7, 3, then the CNT is 3. You use 3 times this num is how many core you selected. And of course, here you use this mean function because maybe you shouldn't build these towers. You should build M towers because there's not enough M. Then you minus change this M. Then you finish. You see, this logic is very easy. You can use 10 minutes or 20 minutes to finish that. And this algorithm, you only got 4 test case timeout. This is called simulation. Okay? I mean, in the contest, maybe you cannot figure out the best way to do that. But at least you can use such way, simulation. And here, the key thing is that you need to use map or set, right? You need to use map or set to improve that, your speed. It's simulation, it's brute force. It seems stupid, but it's good. It's good, okay? It's good. But of course, this we want to go to the full credit, right? Okay, guys, are you okay with this one? Okay, you should okay with this one, then we can figure out the, the fast way. Okay, fast algorithm. Think about that. Okay, think about if in the contest whether you can figure out these such things. Okay. Any question on this one? If got that. Okay. Okay. If we want to optimize that, it's just the observation we do it here. Okay. Let's assume that, the numbers maybe this time I create number 10, 6, 8, 5, and I order them by from the bigger to smaller. Okay. Maybe key is 3. Let's assume M is 8, something like that. The first way we did, maybe we choose this 10, okay? Then we choose this, because key is 3, we choose this 7, and we choose this one. We cannot choose this one, right? We can only choose this 10, 7. We build a 6 group, and something like that, okay? And the next time, you should choose this 8, and on top it is 8 is 6, no, it's 5. You just build this 2 group. Okay, it's so easy. Oh, this is one, one symbols. Okay, and another understanding is like this one. Maybe here, every time, if we do this one, we find each tower, right? We build the towers, and maybe we can change the idea. Okay, we build tower. Each time we need a loop. We need to use loop bound to find maybe lots of cores inside that. That's time out. Let's change the idea. How about for each core, we just choose where it should be. That's the only way, you can get the full credit. Why? Because there is N cores. That's also the experience. What experience? Why we think about this optimize? Because you see here, the N is this number. It's a huge number, right? It's 200,000. I have mentioned before, 200,000 means that your time complexity should be something O(n) times log n, right? Something like that. Something similar like that. That means what? That means you should only loop these core groups once. You should loop them once. Our last exam, we build towers, so we loop this many times. Okay, we build this, we loop this. Although we didn't loop that, we use loop bound, but we loop maybe m times. Each time we use loop bound to find something. That time out. But the change idea is that because n is 200,000, maybe we can just, we can just build the towers. We can just loop these groups once. We loop the group once. For each core, can we choose whether it can add to some tower, right? Can we choose whether they can add to some tower? It's either, okay? It's either. Because m is 8, right? So let's loop once, think about whether we can do that. This is the first core group, 10, 6. 10, 6, we should, because m is 8, we can build all these 10, 6, right? It should put in some tower. Maybe here, I don't know put to where. At least the 10, 6 should put to some tower. Okay, I finish this one. For next one, remember here, because I only loop once, so for each one, you need to make a decision. Whether this 6 core can be added to the answer. Here, your answer added the 6, because you put all these 6, right? And the next, for this 8, 5, can we decide whether these 5 cores can put on some towers, right? Yes, we can. Yes, we can. You see, this is 8, this is 5. First, you cannot put this 8, 5 on top is 10, because k is 3, right? The only size you can put on it is smaller equal than 7. This 8, 5, you cannot put on this tower. This, we call it tower 1. Actually, this towers 1 is a group. Actually, it means 6 tower, right? But this 8, you cannot build on top of it. So what you can do, you can build a tower 8, but you can only build 2 tower, right? Why? Because you already have 6 tower. Then this 8, you can build 2. So your answer, add this 2. You build this one. You see, I have 2 basic. 2 basic. One is 6, one is 2. And the key thing is that no need to think about this 8, 5 again. This size 8 cores have 5 cores. I can decide here, I just, do once, I know. Inside this 5 size 8 cores, only 2 cores I can use, right? Because you cannot build other towers, right? You shouldn't replace this 10 because this has the better answer than this 8 as a base. So I can only get 2 size 8 core built as a base. And another 3 core, I don't use that anymore, right? I finish this record. That's a key thing, okay? If you want to loop once, that means for each record, each element, you need to make a decision when you're doing with it. After that, you shouldn't look at it again. I don't look back at it again. I just finish that. Okay, I build this one. And the next one, I check this one, 7. There is a 13, 7. What I can do, you see, here for this code, I need to decide how I put these 13 cores. Right? So of course, the first thing you think about is put on this tower. This is tower 1, this is tower 2. You shouldn't think about put here. You should put this 7 on the biggest tower. That's a greedy thing, right? You got 7, you should put on the biggest tower, this one. So you put 7 on top of it. And here, because there is 6 tower here, right? So you choose 6 cores from the 7, put on it. So change it to 7. And we didn't finish because we need to figure out all these 13 cores, how we put that. You still have 7 size 7 cores. We put here, And then, can you put here? No, right? Because this is bigger than this one. You can't put here. So it's finished. I only use 6 cores with size 7. I can't put here, right? Then you check this one, 6, size 6, where is 8? So here, when we think about this one, we need to choose which tower it should be on, right? We should put on where? Here is the optimization here. Think about that. Your size is 6. You want to choose which tower, tower 1, tower 2, which tower you want to put. You should try which tower first. Do you need to try all these towers? Right? Nope. We should try this tower first, guys. Right? We should try this biggest tower first. Am I right? Biggest tower first. Why? Because if this 6, you cannot put on this 8. You cannot put on this 7, right? You can't put 7. No, remember, nothing to do with this 10. Nothing to do, right? You look at these 2 tower. Tower 1, the surface, the top one is size 7. Tower 2, the top one is 8. And I got a core size is 6. I think about whether I can put on this bigger one. Because if you cannot put this size 6 on top is 8, you cannot put on top is here. And also the greedy way is that you have a new course. You order them, right? You loop them from bigger to smaller. So count 6 is a bigger one than the undealt one, unsolved one, right? Bigger than is 7, 5 on the future course. So this is a bigger one. The bigger one, of course, maybe you should think about put it on the bigger tower. That's a great idea, right? So, and also this 6, if you cannot put on this 8, you no need to check this 7, right? Why I do this one? There is only 2 towers, you just check them, right? But you need to think about maybe there is 1 million towers here. 1 million towers. If this 1 million towers no order, you want to know whether this core can put on which tower. How you put these 8 cores on some towers. You need to loop all these 1 million towers. That's a stupid thing, right? Maybe you should think about I can put these 6, just start with the bigger one. If I can put on bigger one, I put some on bigger one, then I check the next bigger one. I should check the tower from bigger to smaller. And this tower order by the surface one. Who is on the surface, right? The count size. Because this 10 doesn't matter. I just need to know the tower 1 top size is 7, tower 2 top size is 8, tower 1 this 7 has 6 cores, tower 2 this 8 has 2, right? I know this one, that's enough. Then this 6, okay, cannot put on this one, cannot put on tower 2, so I skip it, okay? I skip it, okay? This means useless, right? And the next one, I got this 5, 10. Same idea. I check the bigger one first. Now this towers 1, towers 2. There is 6 tower has size 7. 2 tower has size 8. Of course, I check this first. Okay, 5 smaller than 8 minus 3. So I put 5, 2 here. This one changed to 8. Right? I put 2 up there. Here, I still need to check this one, the second biggest one. There is 6 core here, but this 5 is smaller, is bigger than 4. So I cannot put this 8 cores here. So I finished. I finished this one. I just got this one. Okay. This is optimization. So each time this, change the angle. I didn't build a tower. I loop each core. I decide how this core can put on the count tower, on which tower, right? I got some cores. I mean, each group cores, I got a size. How many? I got 13 core size with 7. I just need to decide how I put these 13 cores with size 7. Maybe some of them put on some core towers. Maybe some of them put on other towers, right? Some of put on here, some of put on here, maybe. Okay, I just decide which one to put. And to make it faster, here, this one can be just a vector. I just loop each one from bigger to smaller, right? Bigger to smaller. Here, for these 2 towers, or maybe not only 2 towers, actually I should see that tower groups, because here I choose 10, 6. That means you have 6 towers as a group, right? 6 towers as a group. Okay, I just choose which one to put. Okay, and choose which one. There is another optimization is that every time I should choose the biggest top one. At the beginning, this is 10, this is 8, then this 8. This 10 should at the beginning. If I have a new core, I should put on 8 first. If there are still some remaining cores, there's not, I can only put 6 core on 8. If there's more than 6 cores, I can try next one. This optimization makes sure that, each time, if you cannot put on the bigger one, you cannot put on others. So no need to check every one to find which tower you can put the core. I just check the bigger one. No need to try the smaller one first, okay? Try these towers from bigger to smaller, bigger to smaller. And also another thing is that how we save these towers. It seems, each tower has more cores. The observation is that for each tower groups, I only need the surface one, right? If at the beginning is 10, there is 6, 10. Then if I put 6, 7 on it, I do not, I don't need remember this 10. I just need this 7, right? That's enough. Okay, I need that 7, that's enough. Okay, and so for this stat structure, of course, you can still use set, because each time it will ordered. Okay, you can use set. Some guys think that it should use a DQ, okay, that push front, push end. Is that because he find that, okay, this is 10, this is 8. If you put a 7 on this 10, then this tower should change to the back. It's changed to the smallest one, right? Each time you put a new tower, this count group will become the smallest group. Okay, so you do not observe that, that's okay. You can just use set. In your set, you see what? You save this 10, 6, 8, 2. Next time, if you put 7, 6 on top of 10, 6, this 10, 6 should be erased. You save 7, 6 and 8, 2. Next time, if you put 2, 5 on top of this 8, you just erase this one. Now your set only have 7, 6 and 5, 2. So for each tower group, you only need to save 1 pair. That's enough. No need to save all the groups, all the cores in these towers. Because no need, right? Every time you decide this core to put on which tower, it's decided by what is the top one on these count towers. Okay. And there is still some, details. Even you got this one, that's why this one is difficult. Even you got this one, some details you need to think about. At the beginning, if there is 10, 6, and maybe you have, 7, 3, and maybe you have 3, 2, and sorry, maybe it's 6, 8, 3, 2, maybe something like this one. You have 5 group, K still 3, If you want to build M is, seven group, how we do that, right? Think about, we loop each one. At the beginning, you got 10, 6. One idea is that we can build the basic first. There is no tower here. In your set, there's no tower. Currently, no tower. We got 10, 6. M is 7. So we build, okay? 10 is 6 group, 6 cores. Basis is 10. I finish this one because the 6 all here. Next one, you got 7, 3. What happened? See, there is 6, 1. But how many you should put on that, right? How many you should put on that? You have 7, correct? So maybe I should do this one. First, I need to put 1 as a new base, right? This 1 core. I got 7 cores because the M, because the M is 7. See, the M is 7. I use this size 10 cores. I only build 6 towers. It's not enough. So maybe I use 1 course with size 7, build another one. Then I got all the tower here, right? So I change it to 2. Then I continue because this number is not 0. Now I have 2 7 cores. I can put on top it, right? I put on top it. What happened? You have 10, 6, 6 core, you put 7, but you only have 2 cores with 7. You put on top it, what happened, right? So this 1 tower should change to 2 tower. You see, you have 6 cores. 1, 2, 3, 4, 5, 6. Their size is 10, 10, 10, 10, 10, 10. Now I got 2 7 on top it. 7, 7. So what happened, right? You have 2 groups. 1 group, there is 2 7 on top. 1 group, 4 10s on top. So if you want to put 2 7 on top it, erase it, change to 7, 2. And you also have another thing. This 1 tower, you should split to 2 tower, right? You should split to 2 tower. Okay, you should split to 2 tower. Okay, and here still have another thing. This one is difficult. Another thing is that how we deal with the first. First at initially you have no cores, no towers. You have no towers. So how we deal with this one and how we deal with this one is different. Because at the beginning you have, there's no tower here in the set, no tower in your set. That logic may be different. So there is a virtual initialization skill you can use. There's 2 ways. First way, you can separate your algorithm in 2 parts. First part, you just loop to choose which one should be the basic. At the beginning, you do initialize this set as 10. I have 6 cores, and 7, I have 1 cores, 1 group. Why I do this one? Because I do this way, I have 1 plus 6, I have M groups. So at the beginning, you initially build your group. You build your towers, basic towers, 6 10 size, 1 7 size. You build this at the beginning loop. You do this at the first part. After that, you change to this one change to 2. Then you start with the first on 0, 1, right? No, this logic is just what I explained. You have 2 7, for the biggest one. Okay, you can put on it. Then you change it to, you put 7, 2, 7 on top of it, change it to that. But there is 6, 10. So you need also add 10, 4 here. Right? Of course, this is set. You should order. This one may be the biggest one. You can order make the always the biggest one on the beginning. Okay, this is the first one. But this way maybe is not, there is a either way. Okay, the simple way is that a skill we always use. We initialize a virtual element. What is virtual element? We initially we build that there is a size, maybe is a 1 in 9, is the biggest size, and you have M towers here. That's M is 7. You initially, you can assume I have 7 tower. These 7 tower, their size is the infinity, that biggest one. Okay, then I build this tower. Then all these cores can use the same logic because you have towers, right? And what's the logic? You have 6, 10. You check the first one. First one is 1 in 9, 7. Okay, there is 7, 1 in 9. I can put 6 on top of it. So your set change to what? For the first one, your set change to 1 in 9. There is 1 in 9. And there is 10, 6, 10. You see, 7 tower, right? These 7 towers split to 2 groups. One group is empty, actually means. That means 1, and the top one is the biggest one. And another is the 6th, top one is 10. You see, this 6 first number, you got this one. It's right? That means you have virtual one. This is the biggest one. You can put any number on top of them. Then you have 1, 2, 3, 4, 5, 6. Both are 10. You see, you finish this first group. And then for next group, you finish them, okay? You loop to next one, 7, 3. You check the biggest one first. You always want to put the biggest one first. So this is 1 enough, big enough, right? It's just like here is empty. You go to empty. Then, of course, you should put 7 on that. Because only one empty space. You put 7 on that, right? It's just like change this to here. No, you erase this one. You push a 7 on it, 7, 1. Right? You go to 7, 1, just like here. Then there is 2, 7. You put 1, 7 here, 1, 7 here, right? So that means you got 7, 2, just like this 2 group. This is the first one, is 7, 1. This is 2, 7. And also you have 4 group, 4 tower. The top size is 10. So you got 10, 4. You got 3 group towers, just like this one. Okay? And the next 6, 8. Because size is 6, you always check the first one. The first one is 10. Of course, you can put on that. You can put 4 on that because there is 4 core here, right? Just like I put 1, 2, 4, 1, 2, 3, 4, 4, 6 on top of it. So this 4 tower, the top size is 6. So I change it to, because it's ordered, okay? I change here. So this one change as 6, 4. 6, 4, right? This one is 6, 4. And so there is still 4 cores. 4, 6, you check next one. Can you put on this one? No, right? So you leave them. It's just like this one. You still have 3 group towers, just like here, right? 4, 6, 2, 7, 1, 7. Now you go finish this one. You go next one, 3, 2. You check the first one. The first one, just like here, size is 7. The top size, no, I forgot these things, right? Top size is 7. It's 3. So I can put on top of it 3, 3, right? I no need to remember this one because they are only 2. So I finish this one, just like you change 7, 2 to 3, 2. This 3 group just describe 1, 7, 2, 3. I mean the top one, right? You have 1 tower, top is 7, 2 tower, top is 2, 3, 4 tower, top is 6. And I ordered the biggest one is this one. So next time you got 1, 10. think about the first one first. First one is 7, 1 here. So of course I put on top it. So I put a 1 on top it. So this one change, no here. So the group change to, just like here. I have 1, 1, 1, 1. And you change to 9. It's not 0. I can try to put this size 1 to other towers. Where? I check next one. Next one is 6. Put 6 first. So 1, 2, 3, 4. So there is 4, 1. Okay, 1, 4. And still didn't finish. I still have 5 cores. 5 cores, I check these 2. Okay, 1, 1. So there is 1, 2. 2, 1. So 1, 2. Every time the numbers, the second numbers in your set, their sum is always m. So you always have m towers. And these m towers are grouped by the size, 7 or 10 or something. This size means that the top one of this group towers. So every time for each core group, you just try to assign all these cores to different towers. There is m towers. They separate by group. You just choose how many I put on this group, how many I put on this group. But when you put, the best way is always choose the biggest one first. Okay, if the biggest one can't, then you finish that. Okay, then we finish our algorithm. We can use set. But here, one question is here. If we use set, it doesn't work because you see, when I deal with this one, we find that, okay, you see the size can be same because you split some cores. You put 1 on 6, put 1 on 7, you get same size 1. You get same size 1. And of course, there can be same number. Maybe you got 1, 1, 1, 1. That's wrong because set only save the unique number. So that means we can use multiple set to do this one. But if you do such thing, you will find it's still timeout. Why timeout? We check here. Here, just like this one, you may have lots of group. Their size is same, right? Just like here, you have 7, 1, 7, 2. Then if you have a core size 1, you can put here, you can put here. So you may loop all the towers, right? You have more size 1 cores. And now currently, your M towers, maybe they separate by M groups. And this M group, each group only have 1 cores, and their size all 7. Then you need to loop all of them. Put on this tower 1 core, next tower 1 core, next tower 1 core. That will time out. So a easy step is that every time you go to your set, you loop it. If this one same, you combine them, change to 1, 3. And 1, 3 is same as 1, 4, so you change to 1, 7. Why? Actually, you get 2 tower with 1 tower, 1, 4 tower, 1 is 7 tower 1. So this to make sure that your set size is smaller, and every time when you put some new cores on this tower, it's faster. You will not find many towers to put on that. So this, if you do this optimize, you go to the full point. Okay. It's very difficult, guys. So, I mean, if you want to go to the full credit, it's difficult. So that's why I use many time to discuss the first version. That is easy to understand. Okay. So this one I use DQ. Actually, you use set is same. Okay. Initially I put the M biggest tower in these towers. So I keep this DQ on this set every time. All the towers inside it, their numbers, sum is M. At the beginning, I have M biggest one. And every time I loop each core, this is loop each core. For each core, I just check whether this core num is not 0 or it's, cannot put on any towers. I need to use while loop to put it on. Maybe this core group should put on 2 tower groups in the set, or 3 or 4. So I need to use while loop. Okay, it's not difficult. I just find the first one, I just check the number, I just may push the new ones. Okay, I just change something on the tower groups in the set or DQ. After that, I finish that. Okay, and here is the optimization, is I will combine the same size towers into one. If you do not add this for 5 lines, it's still timeout. Okay, still timeouts. And the timeout situation is just same as the first way, the first algorithm timeout situation input case, because if you have m groups, their size may be both 7, but you have m groups, right? Then it will time out. You need to combine them to one group. Okay, it's the only thing here. Okay, guys, think about that. Okay, after the session, I will send this to you guys. Maybe you can also study on that. Okay. The second one, you want to go to the full credit. To be honest, if you want to finish that in 4 hours, right? I think it is difficult. Okay, it's not easy. Even for the experienced one, if you want to get the full credit just in 1 hour or half hour, it's difficult. But the first one, which can got, majority of the score, is easy. You can use half hour to do that. It's just simulation. It's just the map or set, how to use map set. Okay, it's brute force. Sometimes brute force is okay. Okay, and actually this first one and this new one, the difference is just the angle. How do you simulate by hand? Every time you choose tower, right? This tower, this tower, this tower, or you every time you choose a core, assign to some power. That's the different angle, right? Different view you can have. This view comes from where? Just from your by hand operation. You just started that, right? You just start some number, you can find these 2 different ways. At least you can find one of them, right? If you are lucky, at the beginning you use the second way, maybe you got the full credit, right? If you are not lucky at the beginning, when you do it by hand, you think about the first way, then maybe you got full test case timeout. But no matter which way, you should have a way. It's just brute force.